We've discussed the advantages of the dynamic offset or mismatch cancellation. First, the dynamic auto-zeroing can cancel the input offset continuously to minimize the residual offset to tens of microvolt easily. Second, both CMR and PSR are excellent over time, owing to the little residual mismatch over time. Lastly, there's no additional cost or untrimming memory elements needed, but we must measure and cancel the offset in different phases. So the operation must be in a discrete time sampling system, such that the KTXC noise and low frequency noise are increased because of the noise aliasing or folding. How can we reduce the noise besides canceling the offset and mismatch? Think about the modulation and filtering image in a continuous time for 5 seconds. Bingo! That RF systems are converging and down-converging process. For example, the signal is modulated through the passband and amplified. Then the signal is demodulated. Since the data signal information is within the baseband, we should apply a low-pass filter to filter out any high-frequency noise interference to improve the signal-to-noise ratio. Similarly, we can leverage the same idea in the RF modulation and filter to carry off the input offset over the flicker noise without the noise aliasing folding in a continuous time dynamic offset mismatch cancellation. How is the modulation and demodulation in the frequency domain? Correct. The input signal is a baseband signal or low frequency signal, and it goes through the first modulator and upconverts to the harmonic of the square wave clocks. Then the upconverted signal is amplified, and then it goes through another modulator to downconvert back all the energies of the harmonics in the baseband. But what happens to the input offset? Yes, the offset and the 1/f flicker noise only pass the second modulator to get modulated once, which means both have been upconverted to the harmonics of the square wave clock. To make the magic image like RF system, you just apply a low-pass filter with its cutoff frequency above your signal bandwidth, but below all the energies of the 1/f noise and offset harmonics. Obviously, to make the filtering work, the clock frequency for both modulation must be greater than your signal bandwidth. After understanding the magic dynamic offset cancellation in a continuous time, how do we implement the modulator? Think about the switching images for 5 seconds. Right. Intuitively, for the deterministic mismatch over offset, you could swap the polarity of the input signal back and forth at the differential amplifier's input to leverage out its mismatch. To make the right polarity, you must swap the output signal's polarity back and forth, matching the input swap polarity together. In the RF system, we call those switches a mixer or multiplier, but in the offset cancellation technique, we call them a chopper to represent the polarity reversing switch. In the time domain, +1 or -1 from the square wave modulator simply multiply the input signal Vin. How does chopping work in the time domain? Okay, the chopping topology is exactly the same as we saw the continuous offset cancellation in the frequency domain. So let's go through the input signal and offset one by one. The input signal Vin, in this case, passes through the first chopper and converts into the square wave. The square wave signal is amplified in a larger square wave. Then, the larger square wave signal goes through the second chopper to get back to DC at a bigger level. Since the DC signal goes through a low-pass filter, the DC signal at the output of the low-pass filter should be the same as the input if designed properly. From the input signal's point of view, the amplifier with the chopping operations still behaves like an amplifier without any difference. For example, a small DC signal at the amplifier's input will generate the larger DC signal at the amplifier's output. How about the unwanted offset or flicker noise? Yeah, the offset is amplified and becomes bigger at the output of the amplifier. Then it goes through the chopper and turns into the square wave of the chopper's output. Then the square wave offset is attenuated or filtered out by the low-pass filter. So the amplifier with chopping operation is a magic black box of amplifying the input signal, but removing the offset at the same time. Again, the beauty image comes from the fact that the input DC signal goes through the chopper twice and get back to the original DC. But the output offset of the amplifier goes through the chopper only once to convert into a square wave. Ideally, you should see only the signal at the filter's output, and the filter totally remove the offset. But in a real design, you must still see a residual offset. We can discuss the design inside later if everyone is interested. So, what's a real usage in an operational transconductance amplifier? Or how to add the chopper in a 40 cascade OTA? Right, you should be able to add the input chopper at the input of the amplifier easily. But the output chopper should be a tough decision for you. Someone may claim a simple way of adding it to the OTA output directly without thinking about it. Any pitfalls here? Think about the output impedance or the driving strength images for 5 seconds. Bingo! First, the chopper clocks could have a short small time overlap here with both clocks being high, which causes a short circuit impedance and then fail to reduce the gain of the amplifier. Second, the output asymmetrical skewing from the PMOS and NMOS mismatch will cause extra residual offset. Therefore, the output is not a good place to put a chopper. So, where should you put it? Great. The best output chopper is to add a PMOS chopper upside and an extra NMOS chopper down here. First, owing to its fully differential, the choppers will generate match spikes and then a low residual offset. In addition, the output chopper's bandwidth can be large enough for the chop signal owing to the chopping current in the output branch of a 40 cascade amplifier. Therefore, a high effective gain of OTA can be maintained. Third, the choppers are close to the rail, so they are easy to drive compared to the chopper at the output nodes. Lastly, the extra MOS chopper can further chop the offset and the 1/f noise of the MOS current source a lot. Here are the summarized images of why we need a dynamic offset or mismatch cancellation with the chopping technique. Even though the dynamic auto-zeroing can cancel the input offset continuously to minimize the residual offset to tens of microvolt easily, but to reduce the input offset to sub-microvolt, we must apply chopping technique, not only to avoid the discrete time sampling systems noise aliasing and KT-on-C noise, but also remove the flicker noise effectively. The chopping in the frequency domain is like an RF system to up-convert and down-convert the signal back to the baseband. But the 1/f noise offset or interference will only up-converted and filtered by the filter. Similarly, the chopping in the time domain also shows the magic images through the square wave clock, which will move the signal back to the DC signal. But the DC offset or low frequency noise to square wave offset and noise such that could be totally removed by a low pass filter. Lastly, we also provide a case study of adding the chopper into an OTA property to reduce the residual offset and other impairments. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback and please share your comments down below. Lastly, please share the video link with the people who may be benefit from it.